Hi everybody, welcome to the second webinar of Center for Innovation on New Energy. Let me introduce myself. My name is Rafael Vicentini and I have been working at the center since last year. I have been working at the center in Advanced Energy Storage Division, and today I'm going to talking about my two last published papers. These two papers involving the two projects of Advanced Energy Storage Division. One of them is Project 6, Development of Highly Porous Carbon-Based Materials for Supercapacitors, and the other one is Project 7, Characterization of Supercapacitors in Operation Regime. Today's presentation will be in three parts. In the part 1, I'd like to talk about of my paper named Niobium pentoxide carbon shell nanoparticles decorating multi-walled carbon nanotubes as electrodes for electrochemical capacitors, where we have developed a carbon-based material decorated with niobium pentoxide. This paper was published at the journal Power Sources. That journal has 7.4 impact factor. In the part 2, I will show to you my paper named Niobium pentoxide nanoparticles at multi-walled carbon nanotubes and activated carbon composite material as electrodes for electrochemical capacitors. In this paper, we report a carbon-based material, and we had studied that carbon-based material under dynamic conditions. That paper was published at the Journal of Energy Storage Materials. That journal also has a very interesting impact in the scientific community, having 1509 site score. And lastly, I will show to you an ongoing paper. Firstly, I have to thank all authors for the contribution, especially to Professor Hudson for all support that he's given me. At this point, maybe you have been questioning yourself, what is a supercapacitor? Conventional capacitors store energy in an electric field which is modified by a dielectric. Batteries, in turn, use electrochemical redox reactions which involve mass transfer or moving ions. Then, we can say that supercapacitors employs both processes, Faraday reactions and electrostatic reactions. A supercapacitor differs from ordinary capacitors as they use ionic conduction solution between your electrodes. And sometimes they use metal oxides in our electrodes. Supercapacitors are based on the high surface area of carbon-based materials. Then, all of these can improve the energy and power densities of this type of capacitors. Let's look now to some applications of supercapacitors. As you know, a supercapacitor can be used in electric car, airplanes, electronics, and a supercapacitor can be used to store energy from renewable sources like solar cells. In my opinion, a supercapacitor will be used everywhere. Okay, let's go on talking about of part 1. Now, I'd like to show to you my paper involving Project 6. In this work, in this paper, we report a method to produce an unstructured carbon-based material by electrospraying niobium pentoxide onto carbon nanotubes. To illustrate the experimental procedure used in the fabrication of these carbon-based electrodes, these figures are evidencing the electrospray setup and the thermal treatment. But how does electrospray works? In a few words, we apply a very high electric field that attracts the niobium pentoxide to the carbon surface. After that, we have made a thermal treatment at 650 Celsius degrees for 1 hour in constant flow of nitrogen. Because of this, niobium pentoxide was attached to the carbon surface, covering the niobium pentoxide with a thin layer of carbon. And because of this, This paper is named Core Shell, Niobium Pentoxide, and so on. In this presentation, I will just show to you the main results, including cyclic voltammetry, charge and discharge, electrochemical impedance spectroscopy. Okay, first of all, figure A and F shows the scanning electron microscope images. Here, we can see the structure of this carbon nanotube decorated with niobium pentoxide. From figure G to L, we have the transmission electron microscope images. Especially in figure K and L, we can see a thin film of carbon covering the niobium pentoxide. Let's look now to the electrochemical studies. First, on the left side of this figure, we have the cyclic voltammetry or the voltammetric curves as a function of charge and discharge cycles. And in figure B, we have the evolution of the complex plane plots as a function of charge and discharge cycles. Here, in both cases, it goes from 10,000 cycles to 195,000 cycles. And in both cases, the cyclic voltammetry and the complex plane plot, even after more than 100,000 cycles, has a very, very good shape. Okay, second, let's look now to the GCD curves and their corresponding finds. In figure A, we have a classical GCD shape for a supercapacitor. Here, we have used different gravimetric currents. In figure B, we have specific capacitance and area of capacitance as a function of gravimetric current. And lastly, we have the ray gun plot. Here, ray gun plot is contrasting our supercapacitor with other typical electrochemical energy storage devices, like batteries, fuel cells, lithium-ion batteries and capacitors, and so on. Then, after all these results, we can conclude that developed material composed by carbon nanotube and niobium pentoxide has excellent electrochemical properties. Then, in conclusion, we report here a very interesting carbon-based material to be used in a supercapacitor. Okay, now I'd like to move on to part 2. Now I will show to you my paper named Niobium Pentoxide Nanoparticles at Multi-wallet Carbon Nanotubes and Activated Carbon Composite Material as Electrodes for Electrochemical Capacitors, merging Project 6 and 7. In a similar process that was described in the part 1, but now merging Project 6 and 7, we present here a carbon-based material decorated with niobium pentoxide. But now, the carbon material is composed by carbon nanotube and activated carbon. Then, using together carbon nanotube and activated carbon, we can improve the electrical conductivity, the chemical stability, and mainly the cyclability of these carbon-based electrodes. If you look to figure A, the niobium pentoxide nanoparticles was attached to the carbon surface, improving the charge storage process by introducing some Faraday reactions to this process. And again, I will just show to you the main results of this work. These carbon-based electrodes was used in a coin cell to carry out all the electrochemical studies. Then, if you look to figure B, you can see a schematic representation of the coin cell assembly. In the bottom part of this figure, we can see the coin cell bottom cap followed by a spring and the spacer working as electric contact. And next, we have 2 electrodes separated by a mesoporous membrane. And after that, we have other spacer. And lastly, the coin cell top cap that will close the coin cell. Okay, let's look now to some pictures of these carbon-based electrodes. Figure A and B shows the scanning electron microscope images, and figure C28 shows the transmission electron microscope images. Here, we can see the structure of this composite material merging carbon nanotubes and activated carbon. Okay, let's look to the electrochemical studies. First, we have in figure A and B voltammetric curves using different voltage. In figure B, using 1 volt, and in figure B, using 1.8 volts. And the main point of this slide is figure C, on the right side of this slide, where we have the voltammetric curves as a function of charge and discharge cycles. Here, in this case, it goes from 500 cycles to 250,000 cycles. And even after a lot of cycles, the cyclic voltammetry has a very good shape. Next, we have the galvanostatic charge and discharge curves, or GCD curves. In figure A, we can see the GCD curves as a function of the cell voltage, and figure B and C shows the GCD at 1 volt and at 1.8 volts. In both cases, we have used different gravimetric currents, and we have a expected shape for GCD. Okay, from the data extracted from the last slide, we can plot these graphs. Figure A shows the efficiency as a function of the cell voltage, and figure B shows a specific capacitance, specific energy, and specific power as a function of gravimetric current. And from this data, we can plot the radon plot. And again, radon plot is comparing our supercapacitor using this composite material with other electrochemical energy storage device. If you look to the red frame in the middle part of this graph, you can see our supercapacitor. Our results show to us that composite material merging carbon nanotube and activated carbon has excellent electrochemical response, including high specific capacitance, high cyclability, sometimes over than 500,000 cycles, and high energy and power densities. But in this work, in this paper, the main point is the Raman inoperando studies. Let's look now to the inoperando Raman cell. As you can see, figure A shows a schematic representation of the experimental setup used in the Raman inoperando studies. These figures are evidencing the Raman spectroscope lamps and the electrochemical cell. That cell is composed by 2 electrodes separated by a mesoporous membrane. But here, counter reference electrode and the separator has a hole in the center just to the laser reaching the working electrode. And if you look to figure B, on the right side, you can see a real picture of this cell. That cell is named EO cell, and we have been using that cell because it allows the Raman spectral acquisition and the electrochemical test at the same time. Before the Raman inoperando studies, we had made a cyclic voltammeter at 100 millivolts per second. We have made that just to check, just to verify the proper function of this cell. And the right side in figure B, we can see the inoperando Raman spectra at 1 millivolts per second. Here, we had used a voltage window of 0 to 1.8 volts. And from this data, we can plot these both graphs. And the left side, in figure A, we can see the Raman band of sulfate as a function of applied potential. And the right side, in figure B, we can see the D-band position and the D-band intensity as a function of applied potential. In this graph, D-band position starts at 1329 position, and then it goes to around 1335, and then it goes back to initial position. Here, we can observe a reversible shift on D-band position, and maybe in this work, in this paper, we found a relationship between D-band shift and charge storage mechanism. After these finds, I had questioned myself, what means the D-band shift? Since then, I have been working to better understand this point, and I have been studying the fundamentals of the Raman spectrum. I have been trying to understand why it happens, or why the D-band shifts under dynamic conditions. In this way, we have been doing tests under dynamic conditions using graphite. And maybe you can ask to me, why you have been using graphite? There is a simple reason to that. Graphite has only carbon bands on Raman spectra. And because of this, we have been writing a paper named Origin of D-band reversible shift on Raman spectra of graphite electrode under dynamic conditions on electrochemical capacitors. This paper only involves project 7. Let's look now to some results. As I showed before, this figure shows to us schematic representation of the experimental setup used in the Raman operando test. But here, if you look into the cell, in this case, the cell is composed by 2 graphite electrodes separated by a metal porous membrane. Okay, in this work, we have been using 4 different lasers, like 7-8 nanometers, 6-3 nanometers, 5-40 nanometers, and 4-8 nanometers lasers. And we have been using these lasers with 4 different electrolytes. As you can see from figure A to D, in this graph we have the Raman spectra acquisition at using acid sulfate. And from figure E to 8, we have the Raman spectra using lithium sulfate. And figure I to L, we have the Raman spectra using sodium sulfate. And lastly, from figure M to P, we can see the Raman spectra using potassium sulfate. But maybe you can ask to me again, why have been using 4 different lasers and 4 different electrolytes? We have been using that just to check, to verify if the ion size or the laser frequency can affect the D-band shift on Raman spectra. From the data of the last slide, we can plot this graph. Here, figure A to C shows the D-band as a function of applied voltage. And here, it's very clear that the D-band has a shift in your